Welcome to the 18th Annual Walker L. Cisler Memorial Lecture Series. I'm Xiaoping Moore. I'm the Dean of the College of Arts and Sciences here at Lawrence Tech. This lecture series was established back in 1995 with a very generous grant from the Holly Foundation to honor the Detroit industrialist Walker L. Cisler. For those of you who don't know who Walker L. Cisler is, he was a mechanical engineer, graduated from Cornell University. He was also a business executive and a founding member of the National Academy of Engineering. From 1954 to 1971, he was the CEO and chair of the board for Detroit Edison. And one of Mr. Cisler's passion is science education to the populace. And there's a quote from Mr. Cisler: "Science, engineering, technology, and accordingly the country cannot prosper until we once again produce a truly scientifically literate populace." So with that, our goal of this lecture series is actually to promote science education in the Metro Detroit area. And so every year we bring in eminent scholars from different fields from around the country to come to our campus and to lecture to us on a variety of topics. And today we have a very, very special speaker for you. And before we introduce today's speaker, I'd like to introduce our President, Dr. Verinder Mottgill, who would like to say a few words of welcome to you.
Thank you, Dr. Moore, and good evening. Are we here? Good evening. Okay, thank you. I know it's cold, and I appreciate you being here in a weather like this. I think this also proves your commitment to science education. And this lecture, actually, if you read what is on the screen, it fits so well with our initiative of STEM education. Many of you know that we were very fortunate to get a very substantial cash grant from an anonymous donor who impressed upon us the contribution of our great leader, our fourth president, Dr. Marburger, that the STEM Center be named after him, which will be called Dr. Richard Marburger STEM Center. So please acknowledge that great thing. Thank you. In the spirit of this lecture and what you see and what you read here, I think it is very true that we live in the times that this country and this region will actually go forward and prosper based on knowledge-based economy. Those days are gone when people with middle school education could make good money, have two homes, one in Upper Peninsula, one here, because they were physically oriented and they were hard workers. Even those find that without education, there is really no future for this country and our people. So STEM education is a step in the right direction, but science, which is a mechanism of rationale, is so important in whatever field you choose to be. So this lecture is very important for that purpose. We are very pleased with your presence, and I'd like to acknowledge George M. Hawley. The dean mentioned a little bit because he was the pioneer. This lecture is actually supported. It's free to public and was founded at this university by a generous gift from Hawley Foundation. And those of you who are associate or maybe present, we appreciate that support. George M. Hawley was a pioneer in automotive industry, as the dean mentioned. He founded the company, and we're very grateful for this very important gift to this institution and to our region and public so that we can engage in intellectual pursuit. Many of you know in theory and practice motto that we do have an issue at Lawrence Tech which makes us distinctive. That is that our students simultaneously learn theory and practice. And that issue may sometimes mistakenly indicate that this is more inclined toward trade. No, we are intellectually driven. I think this lecture brings home the fact this is a university. And in a university, new knowledge is created and shared. And College of Art Sciences takes leadership in that propagation of knowledge, creating new knowledge and dispensing. Therefore, we have country's leader come here during this lecture and share their knowledge and their experiences with us. So with that, I'd like to welcome some very important partners that we have in this community. I want to acknowledge AGBU Alex and Marie Manoogian School Board of Trustees who are with us. Some of you may know that with Dr. Marburger's leadership, we have made some advancement and progress in working with area schools, high school, middle schools, because we want to bring new talent into science, engineering, math, and other disciplines, so that when they reach high school level, they are already tuned to science, engineering, mathematics, and similar life sciences subjects. So with that, if you help me welcome, let me start with Ms. Diana Kazelian, Principal, Elementary and Middle School. Would you rise and be recognized? Thank you. Dr. Josep Torozian, Principal, High School. Thank you. Ms. Alice Naigogosian, Trustee. She's not here. We wish her well and thank her. Ms. Esther Leon, Trustee. Thank you. Ms. Janice Torozian, a Trustee. I know she's on way. If not, we wish her well as well. It's a weather that is quite challenging. Dr. Linda Darian, Caribbean, Trustee. Thank you. Mr. Richard Karjanian, Trustee. Thank you. Mr. Robert Stepanian, thank you, Trustee. You got to forgive me, English is my second language. Edmund Azadian, Trustee, thank you. Mr. Osef Safarfian, right? And Dr. Richard Marburger, Chairman, Board of Trustees of the school. Dr. Nadia Sarafian, Principal Emeritus. Ladies and gentlemen, we are very blessed with your presence. These are special guests. You all are special, but we are able to recognize the community coming and participating in this intellectual pursuit. Thank you very much. I now invite Dean Moore back to the podium.
So I just want to explain how we select our speaker every year. It's actually a year-long process that started a year before because these people we invite are so difficult to get. We have a standing committee that help nominate in the selection process. So I'd like to acknowledge them. So Tracy Cash Thomas, can you raise your hand? And representing natural sciences, Jeff Morissette, Dr. Jeff Morissette. And representing humanities, Dr. Gonzalo Munevar. I think he's here. And representing math and computer sciences, Dr. Lior Shamir. And now I would like to invite Dr. Shamir, Professor of Computer Science, to come up here to introduce tonight's speaker.
Thank you, Dr. Moore. It's really a great, great honor for me to introduce Dr. Djorgovski. Now, I know that he's a professor of astronomy from the California Institute of Technology. I know that it's common when introducing a scholar, normally you mention some affiliation, mention some major accomplishments. I'm not going to do that this time. First, because the list is just too long. We only have 1 hour. It's not going to scale. But the main reason is that if I did that, it would have given the impression that Dr. Djorgovski is another excellent researcher, and that would be unfair to him because he really belongs in a very small and exclusive group of people who are not measured anymore by publications or citations or grants or affiliation or any of those other matrices that are used by and for the average researcher. And I did look up the numbers. They're ridiculously high. They don't even mean anything anymore. Nobody in the field really needs to know how many times he was cited to feel that the impact that he made on the field. Many people feel his impact every day on a daily basis, and he's not just a great researcher, he's not just doing research, he's changing the way research is actually being done. Just the concept of the virtual observatory, that's a concept that changed astronomy research forever. Astronomy will never be what it was before the concept of data virtualization was introduced. And time will tell, but that it by itself could be a milestone in astronomy research, just at the caliber of the invention of the telescope. That's how big he is, and we're really fortunate to have him here. Thank you.
Well, Dean Moore, President Mudgill, Professor Shamir, ladies and gentlemen, thank you very much for being here. It is a pleasure and an honor for me to be here and give the Cisler Memorial Lecture. I am trained as an astronomer, but actually, and I'll use some astronomy here, but more recently, I've been moving into a somewhat different direction. I think that we're in the middle, or maybe even just at the start, of a profound transformation, and I'd like to tell you about it. Now, this is all futuristic, and probably like many of you, I grew up reading science fiction, and you know, science fiction would be all about rockets and flying cars and stuff like that. Well, yeah, we have some rockets, we don't have flying cars yet, and do we know why? Oh, here we go. But that's not what future turned out to be. Instead of that, the dominant technology of our age is computation and information technology. And that too has changed the world, although sometimes in unexpected ways. So if you had a time traveler from present day go back to 1960s and tell them what the future is really like, they probably wouldn't be so impressed. But more seriously, what is going on is now truly extraordinary. I think it's historically unprecedented. We're in the middle of what's something that's like a combination of the Industrial Revolution and the invention of printing combined, but occurring at a much faster pace. There has never been anything like this in history. So it all started with internet, really, and web, and the world today is vastly different than it was just a couple decades ago, thanks to that. Now, there is a somewhat naive, old-fashioned view how things work, that you have theory that makes predictions and it's proven by experiments. That's a lie. Experiments always disprove theories. And then that gets translated into practice and technology and helps the society. The real process is what I call this virtual helix of progress. The theory and experiment feed off each other constantly, interacting. And then science and technology constantly feed off each other. So for example, 1950s, some physicists at Bell Labs came up with a thing called transistor. And then this laptop here has, a few bazillion of those, and I'm using it to do my research. So technology drives progress in science by enabling us to do things that we couldn't do before, and then science comes up with great new concepts that eventually get translated. I think, and then of course, both of those interact with society, which funds both and benefits from both. So we have never been moving faster up this virtuous helix. So I titled this talk, Science in Cyberspace. What I mean by this is really what's behind your computer screen. And it's a conceptual space in which all of the human information lives. The great philosopher Karl Popper called that the world 3, but let's not go into those details. And essentially, if you think about it, more and more, we do everything in the cyberspace. A lot of work is done there, education, entertainment, we interact with other people through the internet, and so on. And it's getting more and more that way. So I would say not just science or technology, but all aspects of the modern society are rapidly moving towards greater and greater participation in this metaphorical space that connects us all in our knowledge. So this is why I think there is a sort of unprecedented transformation. And in fact, all sciences in the century are becoming cyber science or e-science or big data science. And the science evolves and its methodology has to evolve as well. And it turns out that there are challenges that are common to essentially all disciplines of science and even beyond science, and that come from the vast amounts of data that are being generated, again, thanks to the technology. They, roughly speaking, fall into two categories. First, what I would call data farming, knowing where your data are, storing them, accessing them, and so on. And then exploring them, finding stuff in your data, because that's what science is all about. It's not about data. It's about knowledge. Data are just a step there. And it turns out that this is a great synergy with applied computer science, because we use their tools to discover new things in every field, physics, biology, astronomy, in vast amounts of data we're generating. But hopefully, by pressing deeper and harder, we actually stimulate development of new and better tools and algorithms to do so. Let me remind you that the World Wide Web began as a mechanism to exchange physics preprints. And when Tim Berners-Lee came up with that idea, he couldn't possibly dream what it will become. So physicists brought you the World Wide Web accidentally, and I wonder what is it going to be the next time. So there is also a talk of what's called the fourth paradigm. What's meant by this is as follows. At first, science began with experiments with Galileo and other people of Renaissance. Very quickly, analytical theory, in the modern sense, became part of scientific method, starting with Newton and onward, Einstein, all the famous names. So of course, we still use theory and experiment. But then in mid-20th century, something new came along, computers. And the picture there is of John von Neumann, a famous physicist, mathematician, computer scientist. And at first, computers were used to do a lot of number crunching, to do numerical simulations of exploding bombs or what have you, to solve lots of partial differential equations really quickly. And we still do that. But then sometimes circa 1980s or thereabouts, we began to see a different kind of computing that is data-oriented. And picture there is of Jim Gray, late great computer scientist, winner of Turing Prize, which is computer science equivalent of Nobel Prize. And he was a good friend, and we miss him very much. Jim called us the fourth paradigm, which is data-driven computing or data-driven computational science. Why is this different? Now think about it. When you sit at your computer today, and in fact you carry one in your pocket, you call it phone, but laptop or desktop, you are never actually computing. What you're doing is seeking and manipulating information, data. Occasionally, there is actually some computing going on behind the scenes. And more, that's what drives computation in science as well. So there are different technical demands, and it's a real different way. People talk about data-driven science. Well, science is always based on data, but it used to be more like hypothesis-driven science, that there is theoretical hypothesis, you design experiment, check whether it's true or not. And now we have so much data, we ask the data to tell us what might be interesting questions to ask because of the phenomenology that's seen there. So everybody's talking about big data. And I think that's an exceptionally dumb phrase, because big data is always more data than you used to have. And there are many definitions, but this is the definition that I found that I think is probably as good as any. All right. But really what it boils down to is science that's enabled by vastly increased volumes, growing volumes and rates of data. So what is big data, okay? Well, I know about astronomy, but I think every field is more or less the same. So now in astronomy, most of the data come from large digital sky surveys. I was guilty of a few of those myself. And they typically generate terabytes to maybe a petabyte. We're going towards exabytes. We have maybe 10 petabytes of well-archived information, probably more. And worldwide, astronomy today generates a few tens of terabytes. Both the volume and the rate grow exponentially. For those of you who know calculus, derivative of an exponential is also an exponential. So it's not just that the amount of data grows exponentially, but also how fast it comes at you. And the doubling time is 1.5 years, which may sound familiar. And that is the Moore's law that describes the information technology. Now, think what this means. It means that in the next 1.5 years, we'll generate as much data as in all of the previous history. Now, I can assure you that our understanding of the universe doesn't double every 1.5 years. And same is the case in other fields, I'm sure. So we have a methodological problem. How do we harness this amazing wealth of information, turn it into knowledge? And I put here a few numbers for your comparison. What is a terabyte? Well, terabyte is 1,000 gigabytes, and human genome is less than a gigabyte. What makes you human is less than a gigabyte. Now, what's the human memory? I've seen numbers differing by many, many orders of magnitude, but I would say the median number is less than a gigabyte. In other words, your laptop has more memory than you do. And that explains a lot, doesn't it, right? You can also think of terabyte as about 2 million books of just pure text. And humans can process information, and that is roughly 1 terabyte per year. It's more in pictures and it's less in text because you cannot read 2 million books per year. But we're roughly of that order. The implication of this is that nobody will be able to see all the data. So in astronomy, we're now in this heavy terabyte to petabyte regime, but we're rapidly moving forward. And we're now talking about these projects called the Large Synoptic Survey Telescope, in which Professor Shamir is also involved, that will do surveying of the sky and generate like one of these sky surveys that we have today every night and compare to what was there before and see new things that change. Then radio astronomers are even more ambitious. They're building the world's largest radio telescope, which is actually a collection of a whole lot of antennas, some of them in South Africa, some in Australia, which raw data will be 1 exabyte per second, which is 1 million terabytes. I remember a terabyte is 2 million books every second. Now, most of those data get to be processed and thrown away right there at the source and reduced down, so at the end of the day, this machine will generate only some petabytes of data per day. And of course, we're pikers compared to National Security Agency, and they're building IotaByte data center in Utah, and you can look up what IotaByte is. So in astronomy, we've seen this amazing transformation over the last 20 years. We moved from subsistence economy, where data were scarce and precious, to industrial production of data, huge amounts of data. And this is entirely due to the progress in information technology because the detectors that we use are governed by the same Moore's law, that's VLSI electronics, and as that electronics doubles in capacity every 1.5 years, so does our data volume, and this has been going on for at least 20 years by now. And what that means is all of the action really is at the end, in the data system, where you do data mining and analyze it and figure out what's going on. So you think of telescopes as great facilities, and that's what it's all about, and you just reduce data at the end. No. Telescopes like Hubble, like Keck, very expensive machinery like Large Hadron Collider, they're just the front end. The real business happens after. This is what scientists work on. And so this is also why we need some new skills. So there is a number of important processes that you can, or trends that you can see. And all of them happen more or less on Moore's scale. But even though data rate growth is impressive, to me, the much more important and more interesting aspect is the growth of data complexity, that we're measuring more things, and we're also measuring it better. Turns out it's that data complexity that poses most of the difficult methodological problems, how to extract knowledge from such data, but also opens new scientific possibilities. If it was just the data volume, no problem. You just buy more computers. Their price performance increases exponentially, or decreases exponentially, and so that'll be fine. But it's the data complexity that requires some new thinking. So we transitioned from data poverty to data glut. And what that means, and it's something that most scientists don't understand yet, is it's like money, right? When you have little money, that money is very precious, but if government prints lots and lots of money, that money isn't worth very much. So when you don't have much data, and that's the currency of the realm, ownership of the data is the important thing. When there are lots and lots of data out there, data are not worth anything. It is your ability to discover stuff, the expertise and the creativity. And we're now moving from massive data sets where you just go and create big pile of bits like human genome or sky survey and then analyze it at your leisure, to more experiments which generate data streams that are coming at you all the time. And you have to process the data and analyze them and discover stuff in real time. So you have all of the same problems you had before, but now you also have to do it really fast. And there are a lot of interesting applied computer science challenges that are involved in that. Another interesting trend is that we're decentralizing data and assets. And so, for example, in astronomy, every major observatory would have its own data archive, and every space mission that NASA or ESA fly has their own space data archive, and there isn't any one place which would dominate this data-driven science because it's inherently distributed. The talent, the collecting of the data is all over the world. So these are interesting trends that are changing sociology of science, and in ways that are not fully appreciated yet. But this note I have here is that understanding of complex phenomena requires complex data. We've done all the simple stuff. Now we're trying to understand complex things like biological systems or climate and so on. So typical modern scientific discovery process would be like this. And illustrating it here with astronomy, but first you gather lots of data with telescope, with gene sequencer, with whatever. And then you do what I call data farming. You have to put them in a way that you can find them, what you got and all that stuff. And we know how to do this. It doesn't mean it's easy, but we know how to do it. That's database technologies. Then it gets to be more interesting. How do you actually discover stuff in these masses of data? And we do search for correlations and patterns and look for anomalies and try to visualize them. And currently, that's where the most technical challenges are, in coming up with better algorithms that will scale with the complexity and volume of the modern data sets or data streams. That then leads into the data understanding, the nebulous point, and that's the methodological challenges. Now, this is grossly oversimplified. There is feedback loops all over this diagram. You always learn something, go to get better data or store them in a different way and so on. But this is roughly how things are going, and it's very much a data-driven process. Now, something else interesting happened. Theory is now expressed as data. We still have analytical theories, all right, but more and more we're doing numerical simulations, trying to mimic in the computer what Mother Nature does out there. In astronomy, this is formation of galaxies and large-scale structures or planets and things like that. Now, people don't do this because they're dumb or lazy, still like solving it on a piece of paper. They do it because it's impossible to do it in any other way. And let me give you a very simple example. Possibly the simplest thing you can think of in astronomy or even physics would be, Newton's law of gravity acting on, say, two mass points, like Earth and Sun. And it's an Everett square law. You can ignore everything else. You can solve that exactly on half a page, or any student of physics does. This is what Kepler's laws are all about. Easy. Okay, let me add third mass point to this. Turns out there is no analytical solution for that system. Poincaré has proven analytically that there is no analytical solution for a gravitational three-body problem. Now, here we have a galaxy of a couple 100 billion stars colliding with another galaxy with a couple 100 billion stars, and it's very clear that there is no analytical solution to this problem. So the only thing you can do is simulate it. You put the right physics in and shake and bake and see what comes out and compare that with observations. And that's how a lot of science is done now. So we're studying more complex phenomena, like biological systems, and we have to mimic them through simulations and compare that with complex data that we get. And that's the only way. So this is interesting, because now output of theory is a data set. It's the snapshot of a simulation. It's not a formula. In the past, output of theory is a formula. You fit some data to it, you're done. But now, theory is data, just as complex and massive as the real measured data. And you have to match them together and compare, and good old least squares is no longer enough. And we need some much more powerful tools how to match modern data to modern theories. So question naturally comes like, is this really new, or is this just same old stuff but with more data? I thought about it for a while, and I think there are two reasons why this is qualitatively different. The first one is the data rates are such that most data will never be seen by humans. Now, if I go observing to Mount Palomar or Keck, traditional fashion, may come home with a gigabyte of data, I can still look at every picture I took. But with sky surveys taking terabytes, maybe petabytes of data, no way, nobody can look at all that. So we need technologies that will do robust and reliable way of storing, searching, cleaning your data, and so on. Now, the more interesting thing in my mind is that we're pretty sure that the increasing complexity of the data hides, and I'll give you some examples of this, structures that cannot be directly recognized or even comprehended by human minds unaided. And so this is where we need to have some new tools that come from machine learning and artificial intelligence. In other words, have computers be our research assistants and help us find interesting things in highly complex data structures. To me, this is where it's really going. And in fact, 50 years ago, great scientist, Licklider, who actually was one of the people responsible for origin of the internet, because he was head of DARPA and he funded the thing, he wrote papers about human-computer interaction and foreseen that we are moving towards collaborative human-computer discovery. Well, back then they didn't have the tools, but now we're getting there. And so this is why we're creating new scientific methodology, not just same old stuff with more data. There is something really different. And of course, it's not just science. Everything has the big data problem. Industry, commerce, security, you name it. Everybody's trying to cope with vast amounts of data and try to discover interesting stuff in it. So what did the scientific community do? About 10, 12 years ago, 15 years ago, we saw the rise of what we call virtual scientific organizations in different fields, and Virtual Observatory was one of them. This was a spontaneous, thoughtful response of, say, astronomy community to this challenge of handling great amounts of data. And this was different in several different ways. They're domain-specific, so astronomy-specific, and they're not institution-based. There isn't a single institution on planet Earth that could dominate data-driven astronomy because you just can't own it all, and it would be dumb to try. And so all the resources, the data, human resources, computer resources, are distributed worldwide. And you need a way to connect the assets and the humans in such a way that you can actually take advantage of all this. So it's a different kind of scientific organization, and that put no end of trouble to some funding agencies in Washington because it just didn't fit the mold. It was not a telescope, it was not a mission, it wasn't an experiment, it's something different. And also, virtual organizations should probably have expiration date. We're now in a mode where you create something, say observatory or university, and you expect it to go on more or less forever. But we're in such a rapidly evolving situation that things that made sense 12 years ago are not so good anymore. Anyhow, virtual observatory concept was meant to be this complete research environment for astronomy with massive and complex data sets. Unify together, interoperate different archives, provide the tools, so scientists will do one-stop shopping. Everything is behind your computer screen. Ta-da. Well, it didn't quite happen that way. We certainly made a lot of progress. We managed to put together almost all of the astronomical data that matters in a way that anybody can access anywhere in the world and combine them in some interesting ways. So we began this, well, in 2000. Very quickly that became National Virtual Observatory Project. And then other countries came about, and so now there are 24 of those, and they're unified in International Virtual Observatory Alliance, where people compare notes, they try not to replicate the work, and so on. And so when we called it National Virtual Observatory, we were joking that it's like, to paraphrase Voltaire, like the Holy Roman Empire. It was neither national, nor virtual, nor was it an observatory. But it was kind of profound sounding phrase. So the virtual observatory became real, and now it's a tissue of astronomical research worldwide, even though people sometimes don't realize that that's what they're doing. That when they're seeking data from some archive or literature and so on, they're actually going through virtual observatory protocols, whether they know it or not. So what kind of science does this lead to? Well, one type of science involves data fusion, combining data from different sources, say image sky in visible light, in X-rays, in radio, you have to put things together and so on. You discover stuff in combined data that you couldn't see in any one of those data sets separately. And because you have bazillions of sources, galaxies, stars, and so on, statistics is no longer a limiting factor. The Poissonian error bars are negligible. Systematic errors are important, and you're just in a very different regime from data poverty. Another thing is you can look for very rare, unusual things. If something is 1 in a billion, you better have a few billion sources to find it. And we use this on a daily basis to discover things like quasars, which in pictures look just like stars, but in the parameter spaces, like the one that's shown here, they separate nicely from stars, and you can draw lines somewhere and find out which ones are what. And so this is practical, standard discovery method that we've been using for, at least 15 years now. And finally, this is business of matching these complex, massive numerical simulations with the data. So there is a lot of potential, and people have been really using this in various ways. But from the beginning, we also understood that this can be the mother of all public outreach. Everybody loves astronomy, pretty pictures, and so I coined this phrase, the weapons of mass instruction, thinking that it will get me some money from Washington. It didn't. And we're not the only people doing this. I mean, web has been just fantastic way to proselytize science, educate the public. There are sky browsers like the Worldwide Telescope, like Google Sky. There is all manner of really cool stuff online. And at the same time, we thought, well, we can use astronomy as a bait. People like pretty pictures of galaxies and what have you. But while telling them about this, we can surreptitiously teach them physics too. And then while telling them how we go about this, we can teach them some computer science. And so we've been playing at this a little bit, and I think there's a lot of potential. Unfortunately, education isn't funded nearly as well as it should be. But we have some powerful tools and data to be deployed for this good societal purpose. But what I think is maybe the single most important consequence of all this is as follows. You're probably familiar with Tom Friedman's book, The World is Flat. The premise of which is having this technology evens the playing field, and anybody in the world with access to internet can run your business or whatever. Well, the same thing happens now in science. Now that we put essentially all of our data online for free, and now we're providing tools to explore them, anybody, anywhere with an internet connection, and that means anywhere in the world, because you can use your cell phone as an interface, and everybody in the world except me has a cell phone, and you can do first-rate science. So you don't have to be at Caltech or Princeton or Harvard or a place like that. A smart student at Lawrence Tech University or any small school anywhere in the United States or in India or in Africa can do the same science. We have same opportunity. Now, because human talent is distributed geographically much more than money, this is really important, because you can recruit a much broader pool of talent into doing first-rate science, which you can be observational astronomer without ever touching a telescope. And that's also good for countries that don't have expensive toys like we do. For example, India. India doesn't have any telescopes to speak of, and the climate's not good for that. There are a couple small ones and stuff. But they have a lot of smart people, and they're also good with computer software by and large. And so this is custom built for them. So I helped a good friend of mine, Ajit Kimbavi, to start Virtual Observatory India, and they've been a real contributor on a global scale since then. So this is a strategic issue for science. If, in the past, and still, if you want to have top-notch experimental facilities, you have to pay lots of money. And those now going with price tags of billions of dollars or euros or what have you. And not everybody can afford it. Just consortia of governments can do that. But on the other hand, here is technology which is essentially black magic with Moore's law. And somebody else has paid for it. If scientists had to pay to develop internet, we would never be able to do this, right? It's because it's driven by all the commercial uses. And so we are riding the tiger for free. It is by far the most cost-effective way of doing science for anyone, anywhere. Well, what next? Over the last few years, we saw something a little different. Virtual organizations were useful, but they're kind of getting stuck in certain modes of work. And we need to have a much broader uptake by the community, both as users and as contributors. And so the whole manner of different science informatics fields was coined together, bioinformatics, geoinformatics, now astroinformatics. And the purpose is to bridge the applied computer science engineering with domain fields like astronomy or biology or what have you, and bring these tools to scientific use, and then feedback tries to stimulate their development. So this is a good, inclusive thing. We've been pushing this for the last several years, and it's getting broader acceptance worldwide. But it's also a really good way for scientists from different disciplines to talk to each other. I go to a lot of so-called e-science conferences, and I'm fascinated to learn how people in biology or any other field, climate change, are using some of these cool tools. I always look at, can we learn something from them? Can we do something that's using same type of solution and so on? Well, there are many different challenges that we're all trying to tackle, but let me just point one of them, and that has to do with visualization. Now, this, I think, is probably the single most important obstacle in the way of big data science, because to really understand something intuitively, you ought to be able to visualize it in some way. And philosophers since time immemorial know how to know about this. Well, simple data you can easily visualize, plot X versus Y plot or something. But now we have these incredibly complex multidimensional data sets which have tens, hundreds, or thousands of dimensions. How do you represent structures in thousands of dimensions on a two-dimensional screen or paper? Well, you can't, right? But we can still do a few things. Now, if you think about this, well, typically, in astronomy at least, dimensionality of data sets from sky surveys is of the order of hundreds to maybe thousands. In biology, it's more like in tens of thousands and up, and this is going to grow. So it's not just being able to recognize something. You have a fantastic pattern recognition engine in your head, but also interacting with rigorous data mining tools and algorithms. You have to know what you're doing. You have to see whether the data are distributed in a way that you assume they are. For example, your fancy algorithm may assume that everything is distributed as Gaussians, and in reality nothing is. And so it's the usual garbage in, garbage out. If you misapply the tool with wrong assumptions, you're going to get misleading results. So there has to be interplay between visualizing data and applying these modern computational knowledge discovery tools on them, but things get to be really troublesome once you have many more than 3 dimensions. So you can say, well, you know, wonderful, we got all this data, paid so much money for it, but now I can't discover anything in it. So this, I think, is really, really important problem. And if you think about this, what's the science about? Science is about reducing complexity of observed phenomenology of the world into a set of simpler rules, which we call the laws of nature. It began with Isaac Newton and his laws. That was pretty damn successful, but there aren't very many more successes like that. And this is because a lot of phenomena out there do not obey simple laws. They obey some much more complex sets of rules, many of which may not be expressible in a closed analytical form, which is why I think we'll never have an analytical theory of biology. Biological systems simply are not analytical, right? And so how do we do this? And now we're getting in a regime where the data are more complex than humans can understand. Now think a little bit about this. So now what do we do? Which is where the machine intelligence comes in. Now this is not science fiction. You are talking to artificial intelligence every time you use Google or many other things. Somehow it knows what you want. Well, I call it science on carbon-silicon interface, how the carbon brains and silicon brains get to work together. And there is any number of uses that we've been exploring for automated classification and so on in data sets. All kinds of data mining, there is interaction that I can train an algorithm to separate stars from galaxies or galaxies of different kinds, and then computer can do it, and then I can correct it, and so on. So there are many different things, and I won't go into any details, but essentially every aspect of data-driven science with a growing complexity will require at some stage you have to use some smart machine tools to help you navigate through data and discover interesting things and draw your attention to it. So remember the 4th paradigm, all right? So here is the answer. Why is this something qualitatively new and different, not just same old science with more data? Well, first of all, the information content or complexity of modern data is so high that you can make many, many more discoveries than people who took data for a particular purpose ever envisioned. In astronomy, we've seen this easily with sky surveys, that they feed hundreds, thousands of different studies, most of which the originators of the data didn't have in mind whatsoever, couldn't think of them. You know, you usually have some scientific goals, and you get the data to answer those goals. Turns out there is so much more knowledge in those data that you didn't anticipate, but somebody else did. Right? The second thing is the data fusion. If you start combining data sets, you start discovering new things. In astronomy, this has been historically done by combining different wavelengths. So for example, quasars were actually noticed as some kind of variable stars, blue stars, and nobody assumed they're anything different from stars. Why should they? Then when radio astronomy started, there were radio sources. Nobody knew what they were. At some point, optical identifications of radio sources were made, and suddenly we had a new, completely unanticipated phenomenon of nature which has completely changed astronomy for decades. This happened several times. So there is knowledge hidden in the data that cannot be recognized in any of the pieces of data sets separately. But when you put them together, it comes together. And then there is this business of complexity, that we must use machine intelligence to help us find interesting parts of this data parameter space. So to me, those three elements, data fusion, data mining, and machine learning, are what makes the fourth paradigm. This is why this is different from the past. So I jokingly call this epistemology. How do we actually learn about the world in the era of computation? And I think there are many interesting questions. I think that no philosopher of science, as far as I know, has been actually thinking about this. And one can ask really specific questions. Is there some kind of threshold on complexity beyond which you cannot do analytical theory, right? Or is there a similar thing for measurements? Is there some threshold of complexity for measurements beyond which humans can't really parse it out? And what does it mean that you understood something if you can mimic in a computer, but you don't know why it got the answer it got? I mean, we've been modeling galaxy formation forever, right? And you put particles in machines, some dark matter, whatever, and Newton's gravity, you let it rip, and sure enough, it makes things that look just like real galaxies and clusters and what have you. So we can reproduce how nature got to make those things. But why that and not something else? You can stare at Newton's law of gravity all day long. You couldn't possibly imagine what galaxy merger might look like, right? So there is emergent complexity in these data. Interesting stuff. Now, so a few random footnotes here. What I'm talking about is what we call computational science, which is not computer science. Computer science is a discipline that tries to put computing on a theoretical basis. Here we're talking about using products of computer science and engineering to do other science. There is this obsession with data, big data, and so on. But it's not about data. That's just the most visible part. It's about knowledge. That's our real job. Data are just incidental to this. And there is this switch from data poverty to data overabundance. And so that, again, data are cheap, expertise is expensive. It's just like hardware and software. You can get better and faster and cheaper computers all the time, but the cost of software does not go down. In fact, goes up, because software equals people. And people don't improve according to Moore's law. This is why we need some new tools. So another way to think of it is that computer science is new mathematics, by which I mean, historically, mathematics provided this universal, logical, rigorous framework that can be used for all sciences to organize their knowledge. And now, yeah, sure, there is mathematics, but now we have these concepts that really come from computer science that, again, can be used to organize and systematize our knowledge. And so it's playing the same role as mathematics used to play until 20th century. Which also means that there is this crazy mixed metaphor. It's an interdisciplinary glue or lubricant. It's very hard to do interdisciplinary science because people have different assumptions, different language, and so on. But because we all have to deal with massive and complex data using this emerging new scientific methodology, just like we all use same mathematics, we all use same statistics, this is now the new language, universal language of science. This is how you can have the really interdisciplinary projects studying, say, climate change, or combine physicists and geographers and chemists and whoever else, because there is a universal framework that we can establish to do data-driven exploration. So let me turn now to a slightly different part of the in the end, we have to make our results known. And the way we publish and preserve knowledge has been evolving dramatically, starting from carving them in stone or whatever, and then there is a famous metaphor of cathedral replaced by a book, because cathedrals used to tell stories. And now we have computers. So we've been dramatically, rapidly switching from print-oriented media to completely web-oriented digital. And moreover, the concept of scientific product has been changed. It used to be just papers, describe data, describe theory. Now we have data, archives, metadata, simulations, we have codes, we have all kinds of stuff that simply does not fit in the traditional understanding of what scholarly publishing is. And yet it contains important knowledge. So how is scientific publishing changing? How are libraries changing? What is their role? Is also very interesting. And essentially, it is a switch from owning atoms on which some bits were written, like a book, to owning access to the bits. And it doesn't matter whether those bits are on spinning disk or DVD or future holographic memory. It's the bits that matter, not the medium in which they're written. So we have a lot to do on this front. One other part is how do we communicate? Not just in science, but in general. If you look historically, communications have evolved towards greater immediacy and greater fidelity. You used to write a letter, then Pony Express will take it across the country, then you can publish a book and so on. Telegraph, telephone, radio, television, now it's all on internet. And every step, we got to have more immediate communication and higher fidelity, resembling real life. And so clearly, this is not stopping now. Your cell phone is not the last word. And it's interesting to think, what comes after the internet, after the web? And of course, if I knew this, I'd be a really rich person someday. But so the same now applies to education. It is crazy the way we do education, especially higher education. All of human knowledge is in your fingertips. And so why have traditional lectures? So we've been gradually learning how to do this, use things like Wikipedia, crowdsourced learning, iTunes, there are MOOC companies like Coursera, edX, and so on. There's ever more of this, and essentially harnessing modern technology to help us distribute knowledge in a very efficient fashion, more than any time we could do before. Now, if you had, say, Feynman lectures on physics online, and you do, why would you attend some boring physics lecture that professor who is not Feynman, right? Which brings this interesting thought. And if you ask, what are we for? Why is society paying our salaries? And essentially, it's for these three things. First, we have to discover new stuff and preserve that knowledge, disseminate it. In doing that, we have to be the vanguard of knowledge. We failed miserably in terms of information technology. And then we have to educate people how to use all this and apply it. Well, we're not doing too well. We are still teaching the same way we've done for hundreds or 1,000 years. And the ultimate reason for this is what I call this discrepancy of timescales, that we've never had transforming technology that changes so fast. It changes on timescales of a couple of years, and education is 20 years, and careers are 50 years, and university is maybe a couple hundred years. And this is why we have slow uptake of the new methodology. This is why we're falling behind in trying to teach people properly. And I love this quote from Max Planck, the science progresses through funerals. I'm not advocating killing old professors, but you get my point. Well, then that comes with an epistemological question. Where does science come from? And it originates on these interfaces of human minds with other human minds, or with data, or with some other informational constructs like journals or books. And any technology that facilitates these interactions is likely to lead to better science. So how have we been doing this? Well, in the modern days, we started with simple ASCII text terminals and so on. Then we got into flat web browsers, and now we're getting into 3D browsers, and I'll tell you a little more about that. It's something that Lior has been involved in. what's going on is that I think we're seeing slow rise of the three-dimensional web. Cyberspace you can walk in. And this was cyberpunk science fiction 20 years ago, and now it's becoming reality. And there are already prototypes of this kind of stuff. I was working on some of those, and they look amazingly promising in my mind. But it's just early. It's very early, right? Things are still relatively primitive, but I think the emergent 3D web is now in the same step that, let's say, internet was in 1972 or something like that. Just starting. Well, we've done something about this. We conducted an experiment called Meta Institute for Computational Astrophysics, and it was the first professional scientific organization that was based in virtual worlds. And the question was, how can we use this technology for scholarly purposes instead of just video games? You know, can I use it to discover new stuff as opposed to kill dragons or explode spaceships or whatever? And it was run for a few years, and we learned a few interesting things. Turns out other fields are doing this for research, especially in humanities. Humanities people love this kind of stuff because you can design real experiments with real people in ways that are safe and they're repeatable. It's much easier than going in field. But a lot of other fields are doing it. So what did we do? Well, we had seminars, public lectures, we did research collaboration and so on. And the three important things that come out of it is that for reasons that are not fully yet understood, the subjective quality of this experience is much higher than you think it would be. And is going to be almost as good as real life within 10 years, I think. So it also represents the effective telecommuting and collaboration worldwide at zero cost, no travel involved. Same thing with conferences. This is a big attraction in my mind. If you can really exchange ideas with your colleagues without leaving your bedroom, more or less, not flying across the world and suffering through the airports and flight delays, oh, this is going to be very interesting. So we actually had very serious seminars and discussed things, and we had public lectures, and we have the Nobel laureate, John Matter, give a couple of seminars and public lecture. And one thing that really attracted my attention is visualization. This is partial answer to the exploring of complexity. Now, we have fancy graphics packages that can let you do pseudo 3D plots like that. But it turns out when you can walk into your own data along with your colleagues and interact with your own data and your colleagues in this metaphorical 3D space, you have a whole different intuitive experience than if you were just staring at the computer screen. And people from different fields have been doing this. On the bottom picture is actual data from a sky survey on galaxies, quasars, and stars. And here am I with a colleague looking at it. You know, my avatar in Second Life, I always said, it's just like me, only younger, taller, more handsome, more buff, and more elegant, but otherwise the same. And a friend of mine was visualizing mathematical concept, and this big mess of lines is so-called Lie group, which is actually 248-dimensional mathematical object, which she projected to merely 8-dimensional structure. I have to admit I didn't understand very much, but you get the idea. And so this is why I think this is one of the most interesting emerging technologies of our age, movement towards full 3D visualization of data because it buys you some things that you just can't get in other ways. And the need for this is only going to grow. So we've been collaborating with people at JPL and putting proposals out. They're thinking in terms of virtual Mars. They already have a prototype that is reconstructed from rover imagery. You put goggles on, just like those Lear has, and you're standing next to the Mars rover, and there is Mars around you. And you can walk on Mars. Of course, you're just in the room in JPL, but still, I think there is a lot of promise for this. So I think there's some really interesting practical engineering and research questions that can be So to wind down, science in cyberspace. Everything I do, all day long, I do nothing but sit on my computer, and everything is behind a screen. My data, other people's data, all of our literature, theories, models, my colleagues, everything. I interact with my scientific research more or less only through cyberspace, and this is increasingly the case. It's rare we actually go and have to physically touch a piece of equipment, because it doesn't matter what the equipment is. What matters is the information it produces. And this can only grow. So this is what I really meant by science in cyberspace, and we're just beginning to move on that path. So the old friend I mentioned, Jim Gray, years ago, made this interesting observation that it's in cyberspace, it's like discovering new continent back in 18th century, 19th century. And you launched Lewis and Clark expeditions to see what is on your continent and fill up those maps and find out how can you use the rest of that continent. And so that's where we are now. So that leads me to the final point, which is a fairly broad one. You mentioned, well, you remember that I mentioned these virtuous helixes of progress, of technology interacting with science, interacting with humans, and so on. But it's actually very deep, that we create technology, and it changes us. And this started from before we were human. There's this famous sequence from 2001 Space Odyssey where a hominid throws a bone in the air and spins and turns into a spinning spaceship. So back then, the technology was rocks and bones and sticks, and it gave us opposable thumbs. Technology actually changed us. But now, we have technology that touches us where it really matters, in our minds. And that is going to be a very interesting thing. So we'll see the coevolution of science and technology and humanity accelerate in many different ways. I think we'll be soon talking not about information technology, but cognition technology. So, summary. The takeaway points are that essentially all human activities are migrating to cyberspace, and science is not an exception. And we're not passive consumers of this new reality. We're contributing to it. And there's a hand-in-hand development. We have new needs. We push in technologies to give us those new features that we want, and so on. We share many different needs of this data-driven science with different fields, and this is where interdisciplinary collaboration helps, and it's also been helped by computing. And not so trivial is the fact that information computation technologies are the fastest developing technologies in history, and somebody else is paying for them. And this is strategically the best leverage science or scholarship can have. So altogether, I think we're witnessing slow, well, not as slow as a million years ago, much faster than that, gradual coevolution of society, of humanity, of technology, of science. And this is leading to some amazing future that we get to see. Thank you. I'm told I should go down for questions.
Thank you so much. We have some time for questions, so we have some microphones. I'd like to ask the first question. So actually, your talk made me want to change career to computer science.
Right now.
Now, given the fact that I agree with you that a lot of fields like chemistry, physics, biology, all will move towards using computational science as a way for discovery, do you think that our curriculum should change?
Of course. Yeah.
And historically, at least I know biology, students in biology don't like computer science. And it's a real problem in progressing in that field. So maybe you have some insight as to what Caltech does and what your experiences are.
Should I speak here? Well, Caltech's not yet a good example to follow. We have as much institutional inertia as anybody else, but I think you have put your finger on a really critical problem, that we need to teach students these new research, workplace skills for the 21st century, and we fail miserably in doing that because professors don't know them, right? And we're not talking computer science, computational science, and so we have to develop curricula that will apply these things. It's like, if you teach statistics, you want to teach them how to do practical things, least square fits, tests, and so on. They don't have to prove theorems of converging estimators of minimum variance and whatnot. So it's a very different business. And this curriculum is just beginning to be put together by a few isolated people here and there. I put together a class called Methods of Computational Science. Let me advertise here that with colleagues at JPL, we're preparing to do the first virtual summer school on big data analytics, probably in September, which will be entirely online. And so that means you don't only have 20, 30 students. You can have many, many more. And the materials will stay there forever. Professor Robert Brunner at University of Illinois has some really excellent classes. And I've seen at least a couple different MOOCs that are being put together online. That's a good way to start. But I think it behooves us all to, learn the stuff and then teach it to the students. Right?
Thank you. If you were speaking to a group of high school science teachers, what advice would you give them in addition to what you just said? Talking about integration of science in the class, integration of technology with science in a high school classroom.
Well, I'll tell them like everybody else, they better learn about this stuff. And there are these emerging, slowly, mechanisms, including online classes, that will provide them with at least enough knowledge they can start getting kids interested in it. But this is a problem that it's education-wide. It affects all levels, right? I mean, kids today, they're digital natives. They react in different ways. They think of virtual worlds as the most normal thing in life. And they have different attention spans, and they learn differently. And so we have to change the way we do our business. And I'm not a professional educator in spite of being called professor, but I know that there are people who do research in these things, and I'm very impressed whenever I look at what they're doing. They're really actively poking at all these technologies and see how can they use these technologies to improve learning at all levels, from kindergarten up, I would say, including professors.
The enormous volume of data you have gathered, has it improved the likelihood of life in other planets? And how do you use this information? Because I can gather millions and millions and millions of pieces of data. What's the end result?
Well, the end results are published in papers, and this has been going on more and more over the last couple of decades. People sometimes don't realize that this is what's happening, that they're doing research that's based entirely on data in archives in cyberspace. They didn't took a stitch of those data themselves, and yet they can discover new stuff in it. So this has been naturally progressing. As for your first question, well, yes and no. What we have found recently, thanks to the Kepler satellite, using some fancy statistics, that Earth-like planets in habitable zones are very common in our galaxy. There are probably billions of them in our galaxy alone. Now, that doesn't tell you that any one of them is going to have life, but we are in no way exceptional. The chemistry is same everywhere. Chemical elements are same everywhere. Water has the same properties everywhere. I think it would be bizarre not to see some form of bioevolution happen in similar environments. So sooner or later, right?
There's a question in the back here, please.
As you know, when Isaac Newton was faced with the problem of determining the orbits of planets, essentially solving the two-body essential force problem in the process, he had to develop a new kind of mathematics, namely the calculus, and that inspired the revolution in analytical theory. Of course, which had nothing to do with computers, which they didn't know at the time. Would you say that that the same kind of mathematical revolution could also occur in parallel to this computational developments, and possibly revolutionize the way that we do analytical theory?
I sure hope so. Of course, I don't have a blessed clue how to go about it, neither does anybody else. But I would say one of the hidden science stories over the last few decades is understanding of complexity and emergence. And that there is a lot of interesting stuff happening in nature that we simply cannot tackle a traditional way. I know for a fact that there is no universal theory of such phenomena because I went to ask because I wanted it. And people find a lot of examples of complexity and emergence and so on and study them numerically and what have you, but we do not have anything analogous to the, say, calculus as an analytical framework that happened in the 17th century. Once that happens, that'll be fantastic, but I suspect it will require some very different way of thinking about it. We're just too conditioned by the success of science over the past couple of centuries and stuff that we teach in schools. But sooner or later, somebody will come up.
Hello, Dr. Djorgovski and Professor. I have a question. I know that you once said nowadays knowledge is not formula anymore, but data set, right? I mean, now you once said nowadays knowledge is not a formula anymore.
That's not true. No. We still have same old analytics, right? We're not throwing away anything.
I said this because sorry to bother, because I said this because I watch your videos through the internet. Like you say, knowledge is not a formula anymore, but a data set. So my question is, how can I distinguish the data set as binary automatically gained from the original data that I analysis before the experiment?
Are you saying, can I use numerical simulations to predict something that can be then measured in equivalent complex system? Well, maybe. And knowledge always comes not just as a set of bits, as the data, but as some unifying statement about those data. And that could be just purely descriptive statement that certain type of formula will fit certain part of my data, even though I don't know why that formula and not something else. Now, this is what I call epistemology, that we need to really try to figure out what does it mean, that what have we understood that now we can make galaxies in a computer that look just like real galaxies. Someday there'll be cells made in computer that look just like real cells. But why they took particular forms or not, we don't know that. And so in that sense, the knowledge is not captured yet. But the basis for creating that knowledge is.
I have a question on your viewpoint more so than anything. Do you think that part of the problem when she was talking about how are we going to teach our students to mix science with biology or mix biology with your computing is more so that in our schools we tend to teach that things are what they are instead of trying to get students to look outside the box at this, just because it's written in this textbooks doesn't mean it's right? Like, shouldn't we be teaching more on intuition and not taking everything for what it is but going outside the box instead of just teaching this is this because this formula or this is this because this textbook says so? Don't we need to teach students that now, with all this information that we have now, and the accessibility to it, shouldn't we be teaching that they need to be mining for the information more so than anything, for the right and the valuable things, the valuable data?
Well, there are several things here. I would say it's a bad teaching practice if you just say it says so in the book, and so that's the way it is. I think the real thing to teach students is how to think about it, then give them some facts and explain how did scientists reason from those empirical facts to come up with some conclusion. I mean, to me, that is the real teaching, the real process. Yeah, I'm not sure I understood that. But maybe we can talk later.
Yes? Okay. I was particularly interested in, you mentioned this epistemological debate, right? Mm-hmm. And it's about knowledge. And it seems that with this big data that now we are able to manage more and more, it seems that we are actually changing the way in which knowledge is produced from a stage that was actually, in my opinion, believed by everybody to be more complex and right, which is you have a cause and effect, to a more general analysis of the situation, which is like finding continuities, finding correlations between phenomena. So it seems that this fourth paradigm that you mentioned is going back, let's say. It's just in epistemology from a causation of something that is causing something else, like there is a cause and effect, to just the observation of continuities between phenomena. Like we have this enormous amount of data, then we just observe that this goes with that, but who knows who's causing what?
Well, I'm not advocating that point of view at all. I think what's going on is the data are so rich, and then these new methods are uncovering correlations, phenomena, that you have to explain why they came from. Why is there correlation between this and that? That is not given to us yet. And that, I think, is the part of the intellectual development that we have to do. In the olden days, sure, you can see that there is linear trend between two quantities, and they can think why this is, and maybe you'll figure it out. I think in that sense, this is a straightforward extension of the traditional way of formulating and testing hypotheses, only in a much more complex situation. And the complexity of the situation may be such that sometimes you simply, a priori, we would not be able to wrap our minds around it. There is limit to human intelligence. To go back to search for extraterrestrial intelligence, I remember something Feynman said, and said, well, what can extraterrestrial civilization might be? Well, you look at, say, dogs or cats. They have some intelligence, obviously, but not as much as we do. My cat cannot understand quantum mechanics. Well, okay, no, I can't, but say relativity. So we could be just as limited relative to some more evolved civilization or minds who can easily understand 150-dimensional things. We just can't. And so I think we're really, for the first time, running into what's really deep fundamental limitation of human minds. And this is why we're trying to do this human-computer collaborative discovery. And there are some tools that we can play with, and we don't know yet where this is going to go.
Yeah. I was wondering about the way in which you put together things like data-driven science and numerical simulation. Seems to me those are, or could be, very different things. And I, for one, have not much patience for numerical simulation. For example, I have seen numerical simulations of the brain, and people say, well, we do this, and they will come up with hypotheses and so on. those very seldom panned out because, for example, they say, okay, let's talk about dopamine-driven systems. And they have an extremely simplified system in mind that doesn't really do any justice to the way dopamine works. Like, for example, they don't take into account that there are several kinds of dopamine receptors, and some of them are excitatory, like D1 receptors, and some of them are inhibitory, like D2 receptors. They both work in exactly the same organs in the brain. So this thing doesn't have a prayer to begin with, in my opinion. So when I come to a paper like that, I normally just ignore it because I know the result is going to tell me nothing. On the other hand, what we want is to find out is patterns. And for patterns, we don't really necessarily need numerical computations of any sort. In your own field, in astronomy, people came up with the idea of, when they had a whole bunch of data, to have false color. So if you have two kinds of browns that come together, but they may be created by different elements or ores and so on, they gave one, instead of browns, one was gold and the one was green, and now we could just perceptually see patterns and understand what was going on. See, so it seems like that quite a few things mixed in what you were talking about. Of course, you were talking for only a few minutes.
Yeah, I'm not sure I can do justice to your question, but it seems to me when you talk about modeling of human brain, that's a very ambitious task. I totally believe that it's way too early to be able to do that with any reliable degree. And
I agree.
Yeah, and so the problem is not with the method, the problem is that there just isn't enough data yet. Also, as I understood from my biology friends, oftentimes they don't know what's signal and what's noise. And when you can't tell what signal to noise is, you can't tell what your errors are, and so it's a very early stage. Right?
Okay, I'd like to thank Dr. Djorgovski for a great seminar.
Thank you.
And I think he's very brave to come to Michigan in our polar vortex weather. So we're going to give you something so you can remember us by, which is a Lawrence Tech jersey.
What I always wanted to have.
We have a dessert reception outside, so everyone is invited to the dessert and continue to mingle with our speaker. Thank you. Thank you for coming.